Okay, so welcome to the second unit of the module on addressing mode, instruction set and instruction execution flow. So, in the last unit we have seen what are the basic components of the CPU and the external interfaces and the basic memory structure and how they are all integrated. Now, we will go to the in this module, as we have said, that we will cover the basic idea of how an instruction set is executed, what are the instruction set formats, etc. So, we are now going to the second part, that is required to understand the execution of the memory, execution of the instructions and what are the different instruction modes, that is the main memory. Because as we know that we are all studying about von Neumann architecture. So, in that case all the data and the instructions are present in the memory. So, even if you want to understand about instruction execution, the formats, the sets and different addressing modes and so forth, you have to know the idea of how they are all organized in a memory. So, the second unit of this is the main memory, which we are going to look today. So, now as we have told that this course is delivered in a pedagogical manner or pedagogical paradigm. So, we will see what we are going to see in this unit, that is the unit summary. So, as I told you, we are all looking at the von Neumann architecture concept, which will consist of both the data and the program and the data. So, we have to know about the idea of what is a memory, what is the main memory and what is the secondary memory, etc., and how it is addressed and what is in a nutshell, how it or in a black box, how the CPU interfaces with the memory. There will be in fact a detailed whole module on the memory design, in which you will know the more internals of how the memory works, how it is made up of, how the codes and data are organized there. So, that will be a dedicated module for that. But in this module, we look only at the black box level view of a memory, which will be required to understand how a code executes. So, basically if you look, so memories are divided into mainly two types, internal memory and external memory. So, internal memory basically is the semiconductor kind of a memory, in which case you have a register. So, register is a part of the CPU itself. So, as we discussed in the last unit, so this is something like if you want to add two numbers, so basically they are stored in a memory which is called the register. Then there is something called a cache memory and a main memory. So, actually main memory is the word we have always heard the word called RAM. So, in a layman language RAM, there are a lot of technicalities will come into, but in a layman language what is known as a RAM is basically your main memory. So, basically your CPU or your arithmetic logic unit or the main which is the computing unit of the CPU, basically it can talk only to the main memory, that is it can generate the address and then it can read and write data from the main memory. But actually in between the main memory and the register, so you can think that the CPU or the computing unit is mostly closely attached to something which is called the register. Everything, all the operations mainly they compute at the register level, because if you add two numbers, generally the temporary data or the result will be first stored in the registers and then they will go to the main memory. So, basically it is the most near part of the CPU, but actually the cost of having too many large number of registers is very high. So, therefore, the bulk code or the data executes mainly in the main memory, which can be addressed by the CPU. But there is another memory which lies in between the CPU and the main memory is called the cache memory. So, we will learn in more details about cache memory when we will be going into the full module on memory design. But the basic idea is that whenever you want to refer to some data, generally the address is generated for the main memory, and as main memory is much slower compared to a register, there is something in between which is the cache. So, the cache will get some of the memory, some of the data from the main memory, put it to the cache and they will be used. And again when the data which is in the cache has been exhausted or you require any more new data, it will be coming from the main memory. So, in fact, as of now, if you understand the concept of a register and the concept of a main memory, it will be sufficing to understand the concept of this module and also the unit here. So, in fact, you have to understand that the CPU will generate some memory address which corresponds to the main memory, and the data will be coming from the main memory to the register. For the time being, cache is transparent for our case and so forth. And there is something called the last or the most top level in the memory, which is called the hard disk, that is your external memory. So, external memory can be further more, if you go down the line, there can be tape drives, etc., and there can be bulk SSD hard drives, etc. So, but for our case we are calling in a nutshell, that is a hard disk or the external memory where the whole data will be stored. So, basically this is not a semiconductor type of a memory, generally a magnetic memory. If you are in a broad way. So basically what happens is that whenever you want to execute a code, we execute it from the memory locations from the main memory only, and whenever you want to have something to be loaded which is not in the main memory, then they are all copied from the main memory to the from the hard disk or the external memory to the main memory, and then the code executes. So the idea is that if the CPU wants to generate some address, the addresses are generated mainly for the main memory. So if the data is not available in the main memory, or some code or some instructions is not available over there, it is brought from the external memory. But external memory addresses are not generated as a part of the execution of the code. So for us, most important here are to understand a register and a main memory. Others are actually in fact transparent to understand this module. So now let us go into what will be next in the unit summary, which will be more important to us are basically the main memory. So main memory is a semiconductor memory, as I told you that there are two types basically, one is RAM and one is ROM. So ROM is the random access memory, basically it is volatile, and ROM is the read only memory. But both RAM and ROM are basically random access only, that is not a sequential access. You can access any unit or any word of that memory. But it is from the the name has been carried over as 4, but ROM also can be accessed in a random manner, but read only memory means you cannot write anything over there, and it is non-volatile. So generally the BIOS or some important parts of your code, or which is required for the machine to boot up, which cannot be changed, or in fact we should say that even if the machine is a shutdown mode, when it comes back to power, we will require those codes to be executed are on the read only memory. And mainly the random access memory is exactly what we understand by the term that which is reused and reused, or floating your code, loading the data, changing the data and again writing it back is the random access memory. So now if you look at how basically it works, so generally CPU will generate an n-bit address, because the memory will have some locations which can be done by address. So generally there are 2 to the power n locations, where n is the number of address lines. So that means if there is an n line size address bus, so the number of locations will be 2 to the power n, and by giving an address you can access any one of the data in that location. And again the smallest unit of information is called a memory word. That is, a single bit may not be able to be accessed from a memory. A memory can be organized, say for example 2 GB into 8, that is 2 gigabytes. So into 8 means the memory is organized where each word is having 8 bits. So at a time you can only read 8 bits out of the memory in one cycle. You cannot go for 4 or you cannot go for 16. So that is actually called a minimum smallest addressable information of a memory. That it is not that in a memory which is organized as a byte you can access a single bit. So that is the way how can you access it. And in fact there are two very important registers, one is the memory address register and one is the memory buffer register, which will be used to access the memory. So in fact whichever word you want to access, that address will be given in the memory address register, and whichever data you want to read or put it into the memory, that is written in the or read into the memory buffer register. And in fact data transfer happens to the data bus, and address is sent by the address bus, and there is some control signals like you want to read the memory, you want to write the memory, and then some synchronization, that is read is over, write is over, all those things. So there are some control lines. So in a nutshell, this was the basic summarized notion of a memory which you are going to see in this unit. In fact, the details of how a memory is constructed, how exactly the data is organized, if there is some data which is absent in the main memory, has to be brought from the hard disk. If some memory is not available in the cache, it has to be brought from the main memory. All those details, for that there is a dedicated module given on memory. We will study it later. So what is the objectives of this unit? After doing this unit or studying the unit, you will be able to demonstrate the use of a semiconductor memory which is used in designing the main memory of a computer. That is why it is required. The basic idea you will be able to demonstrate. That is demonstrate in the sense that if there is a code, how it is stored in the memory, how it is accessed, and in what manner the CPU can interface with the memory. Then next you will be, it's a comprehension objective, you can be able to describe how a particular memory address is accessed. Then you will be able to explain the connection of the main memory to the processor to a system bus, that is data bus, address bus and control bus. Then analyze, you will be able to determine the size of a memory given its configuration. That is byte addressable, word addressable, etc. That if I tell you the memory is 1 GB into 8. So what does it mean? So that configurations you will be able to demonstrate, and finally you will be able to explain the read and the write memory operation, that how it is done. This unit is basically giving you a very broad idea of memory, main memory, that is used to understand how a code or an instruction is executed. More details will be in a separate module. So, basically we start, there are two types of memories, one is a semiconductor memory and one is a basically non-semiconductor memory, that may be a tape drive, that can be a magnetic memory, which is generally consists of the external memory. But more important to us is something called the semiconductor memories, because semiconductor memories are faster, you can build them on the chip, but again they are expensive. So, you cannot have a 1 terabyte RAM, that is even not possible by today's fabrication technology, but it will be extremely faster. So, what people do is that they actually gradually, if you go down the memory hierarchy, that is if you go from hard disks to the RAM to the main memory, then to the RAM and then to the register, the size will come down, speed will increase, and of course, the cost will increase. That is what is the idea. So, basically the main memory, which is mainly we are concerned about, and the registers are mainly made up of flip flops, but the main memory which we are mainly concerned about at present are basically of semiconductor. So, basically there are two types of memory, one is the static memory and one is the dynamic RAM. So, static RAM, the access time is faster in SRAM considered to any other variation. Actually, it is extremely fast, generally it may be used for your register design, but the size will be slightly larger because they are actually taking 6 transistors to design. As I told you, at present in this unit we are not going into depth of how the 6 transistors are organized, you will be learning in details in the later modules of the course. There is something called DRAM, which is the dynamic RAM. It is a much access time is higher, in fact that is more cheaper to implement than a static RAM, but the idea is that it actually is implemented with a single capacitor and some register, size will be smaller than the static RAM. So, therefore, you can build larger size of DRAMs in the same price compared to an SRAM, but access time will be slightly higher, but still it is doable. So, in most of the modern days you can understand DRAM is the most widely technology for main memory implementation. Static memory, the size is bit high, so you can think that we can use it for designing of some high speed memories, maybe in the registers or something like that. So, as I told you, most of the RAMs are included using dynamic RAM. So, there are two types of dynamic RAMs, one is the synchronous DRAM and one is DDR RAM. So, synchronous DDR is, as the name suggests, you can read the memory location at every edge of the clock. It may be the positive edge, it may be the negative edge, but any one edge you can read or write it, and that is actually it is said that it is a synchronous DRAM which is synchronized with the operation of the clock. Double SDRAM is also a synchronized operation, but it is more faster or doubly faster than the SDRAM, because in this case you can read and write the memory at both the edges of the clock. That is, you can also go for the rising edge as well as you can do the falling edge. So, the speed of this one will be higher. So, now we are going to look at what is a memory configuration. If somebody tells you that I have a generally memory configurations are written in a product type of manner. So, for example, they have written that 64K into 8 bits. That means what? In this case, I will show you the figure of a memory first. So, the memory basically looks like this. This is as an array, or you can just think that memory is basically an array. So, let me just go back. So, memory actually looks like an array. For a very simple notion, you can think it is an array. So, but there is only one difference, it is a 2-dimensional array. I should say that it is basically a 2-dimensional array. So, for example, we can access say A, 2, 3. So, this we can easily do in case of a C program, but here it is slightly interesting that you cannot do this bitwise access, because I told you in a memory the difference is that you have to access one word at a time, or in fact you can think that it is a 2D memory, but to read and write you have to do one complete row at a time. So, the row is called the word in terms of memory technology. So, in fact, if I say in that way, you have to actually drop this through. So, that means you can access location number 2, 0, 1, 2, then this whole row will be read in the memory, or you can write it in the memory. Individual bit access is not possible. So, you can remember a memory in this manner, that is a 2D array, there is no problem about it, but only thing is that you cannot read a single bit out of it. You have to read the whole row at a time or write a row at a time. So, here it is saying that it is 64K into 8-bit memory. So, what does it mean? It means that the 2D array looks like this is 8-bit. That is, the row size is 8-bit or 8 units are there. In each unit you will be able to write either a 0 or a 1. So, there are 8 bits over there, and that is actually called the one word. And then what is the number of rows in the memory? So, that is actually given by the first. So, it is saying that it is 64K. So, that means it is actually 64 into 2 to the power 10, that is 64 into 1024, that is something like that, this value. So, that means we have 64 into 2 to the power 10, that is 64K, that many memory location, that means that many rows will be available, and each location has 8 bits, that is actually called the word. But in fact, the very similar we can write it as an array of size 6, 5, 5, 3, 6 8, but only thing is that these 8 individual bits cannot be accessed, you can address the whole 8 bits at a time. So, in fact, this will be called as a byte accessible memory, because one word or one byte can be accessed here. And how do you read out the locations? So, how do you access the memory? So, in fact, 0 to memory location starts generally from 0 to 65535, and the first location is all this and the last location is this. So, that is the, if you say, and you have to, so the, anyway, so we say that whenever this is the number, that is the number of rows is this one. So, it is actually 2 to the power 16. So, if you go for 2 to the power 16, then you are going to get this number minus 1, of course. Then actually your bits, I mean bus, address bus size is 16 bits. That means you have to access words from 0 to 65535. So, you need a binary numbers which can access numbers from all zeros to 5535, that is the value. So, it is a 16 bit number, all zeros means the first memory word and all ones means the last memory word, and therefore, the address bus from where the address you will be giving will be a 16 bit bus, which actually comes from this number. And again, but generally it is very cumbersome to write these values. So, we write in hexadecimal notion, that is 0000 hex, that is the first memory location, and FFFF is the last memory location. So, any value if you give, so if I give 0001 hex, that means I am accessing the first memory location, 0 is this one, first memory location I am going to access. So, if I write 0001 hex, that the first memory location is addressed, and depending on the control value of read or write, you will be able to either read all the 8 bits, that is very important to note compared to a 2D array, all the 8 bits will be either read or written at that memory location. Okay. So, as I told you, each location has 8 bits, so the data bus will be a 8 bit bus. So, now when you address, so you are referring one memory location. Now, you have to read or write data from that. So, you require another bus which is actually called the data bus. Now, what is the length of that bus or the width of that bus? Sorry, the width of that bus? It will be the second term. In this case, you can access a word whose size is 8 bits. So, the word size will be 8 bits. So, if the memory is 64K into 32, that means it will be a 4 byte addressable memory. So, the address bus size is 32 bits. And again, very important, basically we are doing two stuff at a time. Either we are reading the memory or we are writing the memory. Reading the memory means we are taking whatever the value is in the corresponding memory location we address to the CPU, and write is the reverse direction. So, there should be a control line to tell whether it is a read or a write memory. So, there will be a single control signal which will tell you whether to read and write. And the figure below, actually this one is our memory. I will come to that. Then again I am saying that how the memory cells are organized, so that a single word you can, single control line will make it read, or a single control line value change will make it write, depends on how the memory is implemented. So, all the details of the internal memory structure we will be looking at in a future, but for the time being the knowledge we are giving for the memory in a very nutshell will be enough to understand how a code executes. So, I told you this is a CPU, it will generate a 16 bit address. Now, why a 16 bit address? Because the memory size is 64K, which is nothing but 0000 to FFFF. And we know that this is actually 8 bits or byte addressable. So, the data bus, which is a bidirectional bus, will be 8 bits. Writing will be from this, reading will be from this side, and these are control signal. So, if it is read write bar, that means if this signal value is 1, then the memory will be in a read mode this way, and if you make this as a 0, then it will be a write mode. So, data from here will be coming over. So, in a nutshell, our memory looks like this. So, now we will study some of the basic semiconductor memory configuration by examples. So, sometimes let me first take the example of 2 GB into, that is 2 GB. So, what is 2 GB? That is 2 into GB means megabytes, sorry, it will be kilobytes, megabytes, gigabytes and terabytes, something like that, right. So, 2, then 2 to the power 10, that is your kilobytes, megabytes and gigabytes. So, 2 to the power 30. So, that is 2 to the power 30. So, that is nothing but 1 GB is 2 to the power 30, 2 GB is 2 to the power 31. So, as you can see, so it is byte bit, so it is, you can see that is 2 GB is nothing but 2 to the power 31, 2 GB is 2 to the power 31 bytes, that is 1, because 1 byte as I told you is 2 to the power 30 bytes, and 2 GB is 8 into 2 to the power 31 bits, because 1 byte is 8 bits. So, the whole memory you can tell is as 2 to the power 34 bits. But again I told you that generally we write a memory in terms of x cross y. that is x is the number of memory locations and this is the width. So, if you are writing 2 to the power 34 bits, that means I am not telling you what is the length of this one and what is the width of the memory. So, you have to tell in which way. So, in this case it is saying the whole size is 2 to the power 34 bits. That is again another way of describing a memory, but immediately you have to tell that it is bit organized. So, what do you mean by bit organized? That means there is only one bit in the row. So, it is a very non-practical kind of a memory. Just to show the example, either you write xy or you can tell the total size of the memory, that is in this case 2 to the power 34 bits. How? 1 byte equal to 2 to the power 30 bytes, 2 bytes, 2 GB is equal to 2 into the power 31 bytes sorry, and then 1 byte is equal to 8 bits. So, the whole size is 2 to the power 34 bits. But I do not know what is the size and what is the size over here. So, in this case it is said is bit organized. Bit organized means there is only one bit at a time. So, in this case obviously the whole length is 2 to the power 34, that is 2 to the power 34 memory locations will be there, because only one bit at a time. Very impractical kind of a memory, only the idea is given to you. Byte organized, this is more or less practical. So, it says that this length size is 8 bits, that is, and in a byte, in a bit organized, individual bits can be accessed, but as I told you, this is a not a practical way of implementing, because generally means we represent our data in terms of 1 byte, 2 bytes, because that is more meaningful. So, you want to access one meaningful word at a time. In this case, you have to add maybe 8 bits one at a time, you have to read 8 locations and then merge it and then understand the meaning of it. So, this is not a very good way of doing it. That is more better that you put 8 bits or 16 bits in one row, get the value and make a meaning directly out of it rather than going in a sequential manner. So, this is byte organized. So, what do you mean by byte organized? There are 8 bits over here. So, what will be the length? It will be 2 to the power 34 divided by 8, that is 2 to the power 31. So, this size is 2 to the power 31 bits, that is 2 to the power 31 locations are there. So, in this case what will be the size of the address bus? 31 bits, because you need to access all the 2 to the power 31 bits. Very simple. Again the same thing we have taken, now it is a double byte. So, why do we actually have different type of memory organization? The idea is that sometimes if you make the memory too wide, then what it may happen that you may be wasting your size. That means say a single instruction takes about say 16 bits or 8 bits, but you can never implement a single instruction or explain the meaning in 1 or 2 bits. So, if you have a 2 bit organized memory, then to find out the meaning of a to find out what is the meaning of a valid word or what do you means a valid instruction, you have to read 8 or 10 memory locations, then you have to assemble them and then you have to find out the meaning out of it. That is not a very good idea. So, generally say we are taking a double byte, that is 16 bit. So, maybe you are going to fit the whole instruction in that. So, just read one word and your job is done. But for example, if I have a 64 bit word, then what will happen? Then one big word will have 1 or 2 or 3 instructions. Then again if you read, you will be reading 3 instructions at a time and then again partition it. So, that is not a very good idea basically. So, what people try to do? People try to keep the memory organized in such a fashion that it at least holds a single instruction or maybe half of the instruction, something like that. So, at least by reading 2 words you can make up the meaning out of it. Nobody wants to do it something like that, they want to put 2 or 3 instructions in one word. That does not look good in a nutshell basically. All these are very broad ideas, exceptions are there. But in general terminology, I would like that all my instruction and data be meaningful in a single word, but sometimes this is not possible, because you all know that to represent a character you require less number of bits, and if you have a value called long int or long float, it takes more number of bytes. But generally it is never like that you have to read 10 memory locations to find out the meaning of a single variable. Maybe 2 memory locations are enough to understand what is the meaning of that whole word or the whole data. So, in this case they are saying double byte. So, that means each word is having 16 bits. So, what will be number of addresses? 2 to the power 34 by 16, that is 2 to the power 30. So, the address byte size is 30 bits. Data bus size will be 16 bits, because your 16 bits you can do together. Similarly, we can discuss for 32 bits also. So, in this case there will be 29 bits. So, what will be the byte organization or the byte organization of the data, the word organization of the data, that size will be your data bus, and total memory size divided by that will give you the number of addresses, with a very simple idea. So, either if you represent memory as 2 to the power 34 bits, then immediately you have to tell what is the byte or what is the organization of the memory, like 2 byte, double byte is the size, or you can write 2 to the power 30 into 16, that is also okay. That will tell you that I have 2 to the power 30 memory locations and each memory location size is 16 bits, that also will be sufficing. So, anyway is okay for us. Now, with this basic configuration of the memory, now we will say that, for example, now we will, as the main goal of this module, we will to understand what is an instruction, how it executes, etc. So, now we will see basically how a memory is read or write is an instruction. A simple instruction, load accumulator 0003. So, what is an accumulator? For the time being, in the last module also, Professor Deka has given a basic idea of what is a register, etc. So, for us, you can understand that accumulator is one of the most primary register, because more or less all the computations are done on a register which is the accumulator. For the time being, just understand that it is the core, one of the core registers. So, load accumulator 3. That means what? Some data from the main memory whose location is 0003 has to be loaded into the accumulator. That is the job. Again, one thing has to be emphasized, that whatever memory location we write in an instruction are all for the main memory. We do not write generally the address for which is the hard disk or the external memory. If some data is not available in the main memory, then it has to be loaded from the hard disk to the main memory, but that is the story we are going to look at later, but not emphasization of this course. So, load accumulator 003, that is how it will happen. So, what it happens is that the CPU will generate this is in the address bus, that is the address I want to read. So, this will be fed to the address bus. Again, the control line has to be made 1, because you have to read from the memory. Then what happens is basically, then while executing the instruction, the memory data, the data in the let us assume that the content of the main memory is 0001, 0010. It is a 8-bit word or a byte addressable memory. So, this value, this 8-bit value will be loaded into the data bus, but it will come through the register which is called the memory buffer register. The address bus, this value will be written in the memory address register. So, memory address register will have the value 0003. So, now the memory will know that this data whatever available in my memory location number 4, that is 0003, has to be dumped to something which is called the memory buffer register. Okay? And then why it has to write, why it has to write to the MBR, because it is a read operation, that is somebody the CPU is reading me. Okay? And then this memory buffer register will put the value into the memory to the accumulator register. So, now let us look at in the figure. In fact, we have not drawn over here, that is the memory buffer register, and there will be a memory address register. Memory address register will be there. So, say this is the content. So, you are giving the value of the signal value, that is equal to 0003 hex in the memory buffer register. So, this one will be addressed, this is 1. So, it will be read, the value will be read to the memory buffer register, from the memory buffer will come to the CPU, that is, and it will be written to something called the accumulator. That is what is the memory operation cycle. So, again I can do the reverse. So, if you say, for example, in this case if you want to say that I want to store accumulator value 3, so in that case everything will be same, except in this case the value will be 0. So, whatever value the accumulator will write to the memory buffer register will be written to the memory location, just a reverse by this one. So, this is in a nutshell again the read and write operation of the memory. So, now let us think that we have a RAM. Maybe we all know nowadays, we know that we are purchasing RAM in terms of slot. So, we purchase 1 GB RAM slot, 4, then we put 4 slots together. Maybe we have 2 GB RAM cards and we put in this. That means memories are modular. So, nobody actually purchases maybe a 16 GB RAM in one chip. Generally, they are maybe brought down into multiple levels, like 1 GB, 8 cards, 4 GB, 2 cards. So, we require modularity of the memories. So, in fact, why it is required? Because then only you will be able to have flexibility. Otherwise, for each design, you may have to make tailor-made memories, which is not actually a very good idea, because I require genericity, and then I want to plug in and plug out to do that. So, for example, say that I want to take a 4K into 16 bits memory. That is, I require a 4K, that is this size will be 4, that is 4 into 2 to the power 10, and this size is 16 bits. Fine, I can make a chip like this for you, but then again I have to design, fabricate everything for you. That is not a very good idea. So, but say for example, what are the chips I am having in the market is say 1K into 8 bits. So, that is a byte addressable memory is available and only 1K memory is available. So, using this basically I have to design my required memory. So, that is you have to modularly plug in and do slight changes and the design should be ready. All memories basically follow a modular design. So, let us see basically if this configuration is given to you, so how do you do it? So, in fact, you see 16 bits and this is 8 bits. So, naturally you have to put 2 together. There is no other way we can do it. This is 8 bits and this is 8 bits. So, the data bus will read parallelly. It's very simple idea that we will have 2 8 bits here, 1 8 bit here, and then both of them will be reading, there will be 2 data buses, and finally we will merge the data, which will be a 16 bit, this is 8 bit, and this is 8 bit. This part is very simple and it can be easily done. Okay, now the next part is that, but we have only 1K memory size, but we require a 4K memory size. So that is what is the trick. So obviously 4 and 1, very simple, you will say that I will put 4 in a row, that is I will put 1, 2, 3 and a 4 in a row. So this one will be 1K, this one will be 1 to 2K, this one will be 3K, and this one will be 4K. This 0 to 1K, then 1K plus 1 to 2K, and so forth. So that will be done. But now 1K means what? 2 to the power 10. So the address bus, this one is 10 bits, the address bus, this one is 10 bits, this is 10 bits, and this is 10 bits, right. So 10 bits address bus is there, and you have 4K. So it's a 4K memory means 2 to the power 10 into 2, that is equal to 2 to the power 12. So in this case the address bus size is 12 for the overall memory, because overall memory is 2 to the power 4K, that is 2 to the power 12 into 16, that is the overall configuration. Okay, so this one is 16 because you have now put 2 in series, and in fact there are 2 others. These are needless to draw because these 2 are happening in parallel. But now I have to access these 4 in a serial manner, because here the number of bits is 2 to the power 12, because that is 4K. But each individual block is size of 10, 10, 10, 10. So what I will do, this 12 bit memory bus, the LSB 10 I will connect to all. That all the memories I will be accessing in the 10 LSBs of the address bus will be connected to the 4 memory. Then 2 MSBs are available. So if I say that now I have to put a logic that when I have to select this row, when I have to select this row, when I have to select this row, and when I have to select this row. The idea is very simple. So if, as I told you, the first memory cell or the first memory block will be accessed from 0, 0, 0, 0, that is from 0 to 1K. The next will be from 1K plus 1 to 2K. So that means what? If the memory is 0, 0, 0, 0, maybe all 0, 0, 0, these are 10 bits, all 0, 0, 0, then the first memory block will be selected. Again, if it is 0, 1, then all 0, 0, 0, 0, 0, that is the next memory block. That means when all this corresponds to the first memory block. Okay, till how much? It will be till 0, 0, 1, 1, 1, 1, 1, 1, 1. So this is the again 10 bits. So this corresponds to the first memory, first 2 basically I should say, the first 2 memory cells or the memory chips in the row. Then this 10 bits means 1K is done. So next it will be what? Next will be 0, 1, 0, 0, 0, 0, 0, this is 10 bits. That is the next number for this. So immediately in this case, these 2 blocks has to be selected till what? Till it will be 0, 1, 1, 1, 1, 1, 1. This is again 10 bits. This will be selected. Next it will be 1, 0 and 0, 0, 0, 0. So if the LSB2 is 0, 0, then this one is selected. If the MSB, if the MSB is 0, 1, these 2 are selected. If the MSB is 1, 0, these 2 are selected. And if the MSB is 1, 1, MSB of the, I am talking about the MSB of the address bus. So now the address bus is 12 bits. So these 2 will be selected. So in a very similar manner, what we do is that we connect the 10 LSBs of the memory block of the address bus to all these 2 cells, and the last 2 bits MSB of the address bus, which is now 12 bits, will be connected to this 4 memory cells in a very nice manner. That is, there is something I have not told you as of now, there is something called a memory select. I will just show you the configuration. There is something called chip enable. So if you look at it, there is something called a chip enable over here. So what do you mean by chip enable? That is, it actually tells you what is the chip can be switched on and off. Like for example, this is the basic configuration. So again I will tell you what the configuration is. So in this case, if you look at it, as I told you, these are 16 bits. So this one will be 1, this is the 2. 2 chips are in sequential. So these 8 bits will be accessed. Now as I told you, if you look at it, this is the one address bus which is the LSB 10 bits. So A0 to A9 of the address bus for the whole chip. So individual size is 1K into 8. So the address bus size is 10. But for the overall, the address bus size is 12. So the last 2 bits A11 and A12 are going to control which chip, which row has to be selected. As you have seen, if the MSB 2 bits are 0, 0, so this one has to be selected. and if it is 0 1, this row 1 0 and 1 1, and all the other bits do not has to be, all the other row must not be selected at that time. So, how can implement? A very simple implementation is a 2:4 decoder, because each chip has something called a chip enable. So, if the chip enable is 1, that chip is operating, otherwise it is not giving any output. So, I put a 2:4 decoder and I give the MSB 2 bits as inputs. So, now if it is 0 0, that means only this line will be 1 and all other lines will be basically 0, because the decoder acts in that fashion. So, 0 0 means the first line, 0 1 second line and so forth will be only 1s and all the others will be 0. So, if the address is say all zeros, that means I have to access the first row of the first set of chip, that is the first row of the, that is the first word, I should say, the first word of the first 2 rows of chips. So, all zeros. So, of course, last 10 bits are 0, LSB 10 bits are 0. So, these 2 are accessed and the MSB 2 bits are also 0, that means this line is basically a 1. So, and all others are 0. So, this chip enable and this chip enable are 1, making these 2 chips on, and all others will be, all 3 other rows will be 0. So, they will not give any output. So, definitely you are going to access this row. Again, let us take the example that all 1s, that is the last row of the chips has to be accessed. So, all 1 means every bit is a 1 of the address bus. So, in fact, all 1 means last 10 bits. So, these 2 bits will be, last row will be accessed, last row will be accessed, last row will be accessed and last row will be accessed. Why? Because 10 bits are all 1s, but now which among these 4 row will be selected. So, again, as all 1 is the address, so this MSB 2 bits are also 1 1. So, MSB 2 bit are 1 1, imply that this row is 1 and all other rows are 0. So, this row and this row will be in a module off manner, and only these 2 rows will be in a module on, that is chip enable, and these 2 will be giving you the data. So, in fact, if you look at it, so this is what is the configuration, that this board line, if you look at it, this board line will access all the chips at a time, because the chips are of size 1K. So, if you have to access any row, say 0th row, 2nd row, 1st row, so all the corresponding or same rows for each of these chips will be accessed simultaneously. So, if you say that 0 0 0 0 F, so all the first rows of all the elements will be selected. But now you have to check correspondingly to the last 2 MSB that whether I want to take from this row or this row or this row or this row. So, if this is 0 0, so only this chip enable will be on and this row will be accessed and so forth. So, this is actually what is something called a modular design, that is you take different modules and arrange them using a decoder. So, if you are given a byte addressable memory and you have blocks of size 8, 1 is enough. If you have byte addressable memories blocks and you want to have 32 bits as the address or as the word size there, so 8 into 4. So, 4 memory blocks has to be put in series, and then depending on the size row you have to multiply by that manner. So, if I write in a formal manner, say for example, you have a block size is 1 byte and this size is also say 1 KB or 1 MB or whatever you want to. Then very easily you understand that if this is 1 byte, so if you have a 8 byte or 8 byte or 16 byte or whatever is the size, then you have to increase in that row, in the row size. That means, if you have say the unit size is x is the word size of the memory blocks available, and if you want to implement a memory whose size, overall size is say 3x in the row, then you have to put 3 together. Of course, if this size is y and if you require a memory whose size is 3y, then you have to put 3 in the column size. Very straightforward. Only thing is that you have to appropriately put a, what I told, you have to put a 2:4 or whatever is required as a decoder, which will select the appropriate row, this row or this row or this row, depending on the memory accessed. So, all the LSBs are generally fed to all the memory chips and the MSBs are kept to the decoder. So, that is what is the idea. So, if I go over this, so in this case all the things that is been detailed out, that 4K is the size of the memory. So, we need to put 4 such in the columns, in the rows. So, we need to require 4. So, 1:4. So, 4 such will be there in the number of rows and the column size is double. So, you require 2 blocks in the column, and then the LSB 10 bits will be connected to the data bus of all the memories, and the MSB 2 bits are connected to 2:4 decoder, and this is what is the memory organization. So, whatever I have told you, you can read the theory which is given in the PPT, and it will be clear. Now, they have given an example that how do you want to read the memory location FFFH, that is 49th row. So, in this case if you look at it, so all 1s will be the memory, and then the LSB 8 bits will be all 1s. So, the last row of all the memories will be accessed, and then if you look at it, the last 2 bits MSB is also 1 1, that means the 4th row will be selected, and that is it. And in this case 2 memories are in series, so 16 bit will be the data bus. So, basically with this we come to the end of this unit on basic black box accessing of a memory. In this case we have not gone into the details of how the memory is implemented, etc. We have tried to show that on this, from the perspective of the CPU, if you have to give the address, you have to read, you have to write, what is the basic data, basically basic infrastructure required, how do you give the address, what are the registers involved, how and it is read and write. Only in this perspective we have played, because for this unit, for this module and the next module, we will be mainly understanding how a code executes. This much black box view of the memory is enough for us to understand. And next module will be fully dedicated on memory, where you will learn the inner details of how a memory is implemented, how it is interfaced, how it is synchronized, etc. So, towards the end, basically if we look at the questions and objectives, so there are 4 questions, or we can have just 4 questions are put over here, and we can just see that it will obviously meet the objectives. Like first question is what are some of the main semiconductor memories used, and discuss the pros and cons. Like we have RAM, we have registers, we have DDR RAM. So, of course, it will cover the objectives where we are able to demonstrate the use of semiconductor memories which are used in the main computer. That is the first question will satisfy the objective, that if you are able to answer the question, this objective will be satisfied. Similarly, we are given a hypothetical memory configuration, and then we have asked how it can be interfaced, etc. within the system bus. So, in fact, this will be covering up the objective on how to address a particular memory in the memory, how explain how the connection of the main memory to the CPU or the system bus, etc. And this is the question on if there is a memory of such size, if it is byte organized, bit organized, how it can be accessed, and what is the basic architecture, what is the data bus size, what is the address bus size. So, I think it can be easily satisfied by this two the objectives and so forth. That is the basic modular design of a memory which we have seen. So, this is the part of it. So, in fact, we have seen that by covering this unit and the very few basic questions, basically we are able to satisfy all our objectives. So, in fact, this brings us to the end of this unit, that is a black box view of a memory which will be mainly required to understand how basically the codes can be executed. Thank you, and in the next unit we will be mainly again looking up how instructions are designed, how they are accessed and so forth. Thank you very much.